At -50 degrees Fahrenheit, metal contracts, rubber shatters, and most modern materials fail in ways their engineers never anticipated. Engines seize. Wheels become useless. The ground turns into a frictionless sheet of compressed ice that laughs at anything with axles. But wood? Wood has been solving this problem for thousands of years, and that's exactly what we're going to use. The mission is straightforward and completely unreasonable at the same time. We have 2 tons of harvested meat, roughly 1,800 kilograms of processed game, and we need to move it across open tundra to a storage location several kilometers away. No roads, no vehicles that can operate reliably at this temperature. No shortcuts. What we have is timber, hand tools, rope, and a working knowledge of how sleds have carried impossible loads across frozen terrain since before recorded history. Before any wood gets cut, the design has to be right. A sled that fails under load in these conditions isn't just a setback. It's a survival problem. The principles are simple, but non-negotiable. The runners must be long enough to distribute weight across the snow surface, so the sled floats rather than sinks. The frame must flex slightly rather than remain completely rigid, because a perfectly stiff structure will crack on uneven terrain. The joints must be lashed rather than nailed wherever possible, because at -50, metal fasteners conduct cold directly into the wood grain and create fracture points over time. And the load platform must sit high enough off the ground that packed snow doesn't build up underneath and create drag that doubles the pulling effort. The wood selection matters enormously. Hardwoods are too brittle in extreme cold. They lose flexibility and become prone to sudden fracture under shock load. The choice here is seasoned spruce for the main frame and runners, with green birch used for the lashing points and cross members where some give is needed. Spruce is light, strong along the grain, and retains enough flexibility at low temperatures to absorb trail impact without cracking. It's the same wood that traditional Arctic sled builders have chosen for centuries, and there's no modern substitute that performs better under these specific conditions. The runners are shaped first. Each one is a single long piece of spruce, roughly 3 meters in length, with the front tip steamed and bent upward at an angle that allows the sled to ride over surface obstacles rather than dig into them. Steaming wood in a camp environment means wrapping the tip section in wet burlap, applying sustained heat from a fire, and bending the softened wood slowly against a carved form, then lashing it in the bent position until it cools and holds its shape permanently. Rushing this step produces a runner that straightens out under the first serious load. Patience here prevents catastrophic failure later. Once the runners cure, the frame goes together. Cross beams are lashed across both runners at regular intervals using wet rawhide, a technique that seems primitive until you understand why it works. As rawhide dries, it shrinks and tightens around the joint until it becomes harder than most wood-to-wood mechanical connections. It also flexes under stress rather than transferring force directly into the grain, which means the sled can twist slightly on uneven terrain without any single joint taking the full load. Modern rope works as a backup, but doesn't achieve the same final tension. Rawhide is the right material for this joint, and the cold climate actually helps it cure faster. The load platform is built from split timber planks, rough, unfinished, deliberately gapped rather than laid flush. The gaps serve a purpose. Flush planks trap snow and ice between them and the runners during travel, adding weight and increasing friction. Gapped planks let loose snow fall through and prevent that buildup. The platform is lashed to the crossbeams, not fixed rigidly, so it can shift a few millimeters under uneven load distribution without transferring stress to the frame structure beneath it. 2 sleds are built to split the total load, approximately 900 kilograms each. This isn't a weight compromise for construction purposes. A single sled carrying 2 full tons would require runner width and frame mass that makes the whole assembly too heavy to pull efficiently across varied terrain. 2 smaller sleds can be separated on difficult sections, moved one at a time, and reconnected for straight open pulls. They also provide redundancy. If one runner fails, the other sled still functions. The runner surfaces need treatment before the load goes on. Bare wood on ice generates more friction than most people expect, and over several kilometers that resistance adds up into an exhausting and potentially impossible pull. The traditional solution is ice glazing. applying a thin layer of water to the runner base and allowing it to freeze into a smooth, low-friction ice coat directly bonded to the wood. In these temperatures, that process takes under 2 minutes per runner. The ice glaze is reapplied at each rest stop during the haul because friction and minor surface irregularities in the trail gradually wear it down. Pulling 2 tons across open tundra in sub-zero conditions is a managed process, not a brute force one. Load positioning on the platform is calculated to keep weight centered and slightly toward the rear. Front heavy loads cause the bent runner tips to dig rather than ride. The pulling lines are rigged at a low angle to maximize horizontal force transfer. Rest intervals are planned in advance because stopping completely in extreme cold for too long allows the runner ice glaze to bond lightly to the trail surface, making the restart harder than the initial pull. When the sleds arrive and the meat reaches storage, the timber frames are cleaned, relashed where needed, and stored elevated off the ground to prevent the runners from freeze bonding to the surface. A well-built Arctic sled, maintained properly, lasts for years of heavy service. The materials cost almost nothing. The knowledge behind them took generations to develop, and at minus 50 degrees Fahrenheit, that knowledge is worth more than any machine money can buy.
The knowledge behind them took generations to develop, and at